Okay, so I'm going to speak with the government perspective on this. We had an exciting workshop, gosh, was it like 2 months ago? It feels like yesterday, and we not only had the DOE, all of the DOE labs represented there, we also had representatives from every government agency that's interested in the future of supercomputing. We had NSF, we had everybody but NASA, I guess. So we had, oh, they don't got no money. Yeah. All right, so for a supercomputing perspective here, people have been saying, Moore's law is not really falling off. Well, I don't know. From our perspective, it really is. This is the top 500 list for the past 30 years. They've been tracking the performance improvement of supercomputing systems using a benchmark called LINPACK, which today we actually consider too easy of a benchmark. It's too floating point heavy and doesn't emphasize memory performance. But nonetheless, the red line is the #1 machine on the top 500 fastest supercomputers in the world list. And the orange is the last one on the list. And then the sum has produced this, fantastic exponential line that historically it's been 1,000x performance improvement every 10 years, like clockwork. Until you look at the last 8 years of data where we've clearly fallen off of those exponentials. And today we're looking at 10x improvement every 10 years. And we've responded by delaying the acquisition of new systems, which makes our suppliers very unhappy. Cray decided to call it in and join with HPE because we said, instead of buying every 4 years, now we're going to buy every 10 years. And that's bad for the whole industry. And so we can't continue on this path if we want to deliver what's necessary for the future of science in supercomputing. And so, of course, computer architects look towards specialization as a way out of this slowed, greatly diminished future. And it's not just a computer architect's fantasy, although it is kind of. It is nature's way of extracting more performance from a resource-limited environment. In the past, we had the powerful Raptor processors like the Xeon and the Power, but when you have food scarcity, and in this case, post-Dennard scaling scarcity, nature responds by having a lot of smaller critters to go after the food sources, and that's exactly what happened. We had the Intel Knights Landing, we have the AMD, Cavium Marvell, and to some extent GPUs. Lots of lighter weight cores, but many of them. But once you get to post-Moore scarcity, then the critters got to go after different food sources, and that's how we end up with these Darwin birds. And this is what we're seeing here at the OCP, seeing in the development of Apple, Google, and Amazon doing their own silicon that's tailored for their needs. Now, how is supercomputing going to plow in this direction? After all, we used to have custom machines for HPC in the past, and we went away from that. This is the classic attack of the killer micros. When I started my career in the 90s, we saw that the rate of reinvestment in custom machines was not able to keep up with the kind of reinvestment they could put in the microprocessor industry, which was growing like gangbusters then. What that led us to drop doing full custom processors and adopt microprocessors as the center of our machine and commodity clusters with custom interconnects. And this was not really a technological solution. It was more about the economic model. The lesson we learned wasn't that you can't customize it. The lesson we learned is that you have to follow the market. And so we have this Branscombe pyramid here where we leverage what the rest of the larger market is doing and specialize only for that 10 or 20% that makes a difference for HPC. But as we look at the economic context today, it's not good enough anymore to understand the technology. You also have to understand the market context. And for the past 30 years, we've been partnered with the microprocessor manufacturers to create HPC and tailoring around that. But if you look at the broader market, it's actually dominated by the hyperscalers, the folks that are really make the OCP. And so the answer to this is really, the bottom line is we should follow the money. The future of HPC is to find out the economic context of what the hyperscalers are doing. And what are the hyperscalers doing? They're doing chiplets, and you're seeing all the stuff that's happening here on the OCP floor. And this is a great diagram I love from DJ Johnny and from Meta. And it basically is saying that the hyperscalers also see their future in specialization, but not specialization at ridiculous costs, specialization using techniques like chiplets in order to lower the cost of tailoring machines for their workload. Instead of being a transistor focus for the future of the industry, moving to a system focus. Or rather than thinking in terms of, oh, we shrink the transistor and everything gets better and drives that economic engine, instead it's specialization, tailoring the machine for the workload and getting economic value in driving the economic engine through those means. So we see the future, so we really see the future of post-exascale computing, not from continuing die shrinks and shrinking transistors, but rather towards extreme heterogeneity where we have a lot of different specializations co-integrated together. But the research question really is, what is the right specialization to include? And also, what's the cost model for integration? And lastly, trying to understand the chiplets ecosystem and leverage the supply chains that the hyperscalers are creating for their specialized future. The dielet becomes a commodity, not the chip. And so, commodity is going to continue to be the future, but it's not the chip anymore. And we want to see what kind of partnerships and economic model to build for the future of HPC. I'm also going to have a quick digression. We also have a lot of the custom silicon that the government, or the DOE in particular, makes is sensors for these advanced experiments. So this is what it looks like in the back room of my laboratory. And we also have giant experiments like this is the Large Hadron Collider. This is about 18 football fields worth of silicon. You can see this tiny person here. This is on the platform servicing the sensor. Each CCD sensor collects data at 200,000 frames per second, and they have tens of millions of them. And we need to be able, but the silicon for the sensors is 65 nanometer technology because it doesn't make sense to make it any smaller for CCDs. We'd like to co-integrate state-of-the-art FPGAs or other data processing things into those sensors to reduce the data in situ, because it's we're talking about petabytes per millisecond, and it's very difficult to do except if we do this advanced packaging technology. So that's also an exciting application. All right, moving on. So as a thought experiment, we decided to take a state-of-the-art HPC chip. This is from our colleagues at Riken in Japan. This is from the Fugaku. And we decided to select Fugaku for chipletizing because it uses licensable IP from ARM. All of the specs are published. And in fact, our colleagues, and it has a nice partitionable die layout, and our friends from Riken shared all of the details about the speeds and feeds and the partition sizes and the power. So in chipletizing, we basically break up the design into these component pieces, and we know what the die-to-die feeds are necessary to make it work. And you could recompose the entire Fugaku chip using these chiplet building blocks. And the great part about it is that we recognize that actually you could standardize on 2 different chiplet form factors. And this would be really great for just logical, physical compatibility. You'd have an 11 by 11 die, and just standardize all of the dielets for the compute-intensive operations in these kind of square die to maximize the compute to shoreline ratio, but also for the I/O-intensive like memory controllers that could be reusable across many different HPC type systems and non-HPC, these tall skinny dielets. And by standardizing around those dielet sizes, it could actually normalize our ability our chiplet ecosystem to deliver in these things. BAPI did some thought experiments also in looking at a technology-centric scaling where we increase the bump pitch each generation and see how that plays out, and also do a capital efficient where we use exactly the same bump pitch like they've done with the HBM for the past 3 generations. In both, you actually have a very there's a path forward, basically, that makes sense that you could go 5 generations using either of these paths, which is very exciting result. So lastly, modular reusable chiplets, it enables us also to do things like take the memory subsystem. We had a project with Lanel with ARM SoC vendor, and it just turned out to be too expensive to take the memory subsystem, which was DDR, and replace it with an HBM memory subsystem to give the bandwidth that we needed for HPC. But had we had chiplets at the time, this would have been a much lower lift, and having SKUs to deliver to different submarkets would have been practical. But moreover, we'd like to see be able to get in and drop specialized accelerators into the package. And this is a very exciting outcome for chiplets ecosystem and for the future of HPC, is being able to insert those HPC-specific accelerators, which is a no-go when it comes to monolithic silicon. They're not going to do another mask for us. And indeed, we have companies like AMD who are actually have a vision for offering us a spot in their package. And this is only possible with chiplets. 3 minutes? All right, well, so this is the big opportunity for HPC. We can't continue doing what we've been doing. Yes, Attack of the Killer Micros said we couldn't specialize and go it on our own, but this is about slipstreaming behind what the rest of the hyperscale industry is doing. We are following the money. This is a way to get specialization while at the same time following the rest of the industry. It's the new 80-20 rule. So the 80-20 rule had been monolithic microprocessors, and we'd innovate in the board. Now the 80-20 rule is innovation within the package, thanks to chiplets. And if we don't move to this economic model that the rest of the industry is moving to, then HPC will no longer be tall enough to attack the city. So that's all I got to say. Any questions? Yeah. Oh, sorry.
I can't figure out how to get it down, so I'll go on my tiptoes. Question for the Fugaku thought experiment. Did you compare, it's obviously back of the envelope maybe, but what did performance look like once you chipletized it compared to the original?
I don't know. Do you want to answer that, Beppy? Okay. No, we're able to deliver 100% on the speeds and feeds at the Fugaku chip, so we made that a design constraint that you wouldn't compromise on the internal bandwidths.
We're happy to share the spreadsheet with you. Basically, I kept the core count cost.
Yep.
That's what we tried to do. And then so how we could increase the core count generation to generation. That was a metric of performance.
Yeah. And there's probably going to be an area penalty. We know from our colleagues at AMD that there's like an 8% area penalty, but you get better yield on the individual chiplets that you're assembling, so it kind of makes up for it. There's a great paper at ISCA from AMD. So.
Thank you.
Yeah. Bill?
Would you mind going to the mic?
Yeah. I think it is important to look the next step. So beyond HPC, how do we go in attacking the rest of the industry?
Mm-hmm. Absolutely. How do we do that? Well, I mean, I'm
looking at your vision.
My vision for the rest of industry, my vision is to follow follow the money. Like I said, the industry's going to do what the industry's going to do. But I do believe that everything that we've heard this morning about the open chiplets ecosystem and actually being able to come together and say that developing this open market that enables us to mix and match the chiplets is crucial for getting the kinds of volumes and the kind of reinvestment that would turn this into a viable ecosystem for the future. Yeah.
Could you please touch on the chiplet, what's churning in chiplets for CXL memory expander ecosystem? Whether there is any momentum that you observe in terms of attaching third-party accelerators from different vendors to CXL-centric memory controllers and poolers. Thank you.
Yeah, so CXL, we've been mulling this over, the HPC folks. The challenge with the CXL and why it's more interesting to look at UCIe is specifically the bandwidth getting to the accelerators. When when GPGPUs started to launch, we could see fantastic performance for individual kernels on the GPGPUs, but getting to transferring the memory for the problem to that GPGPU became a limiting factor, and the CXL expanders right now seem to be targeting like the electrical performance, and we need to somehow go 2 generations forward, like overnight, in order to deliver the kind of bandwidths we need, so that we won't lose all the gains to the data transfers. So that's why co-packaging is a much more interesting path forward from our perspective than CXL expanders.
Do you foresee with the UCI ports over these expanders that
Sorry with this. If you wouldn't mind.
Okay, I got it.